Well, first, I'd just like to thank the organizers for giving me the opportunity to speak here and also to help bridge the gap between solar system science and exoplanetary science through the topic of planetary magnetospheres. And the project I'm presenting today was done in collaboration with Aline Vidotto and focuses on the fate of planetary magnetospheres. And when I say fate, I don't mean what's going to happen next year or in a decade or even in a million years. I mean, what is going to happen when the sun leaves the main sequence? And when the sun or any main sequence star leaves the main sequence, then it undergoes significant transformations. The sun will lose about half of its mass through its winds. Its radius will expand out to where the Earth currently sits, and the sun will increase its luminosity by a factor of thousands. Then the sun will shrink down into an Earth-sized object known as a white dwarf. So what are the consequences for the solar system? Well, Mercury and Venus will be engulfed. The outer planets and Mars will survive, and Earth is right on the edge of being engulfed. We actually don't know, depends on the tidal prescription that you use to determine if the Earth will survive or not. And there are also interesting consequences for the minor bodies in the solar system, which I won't get into in this talk. Now, for extrasolar planetary systems, here is a snapshot in red circles of the known planetary population around giant stars after their stars have left the main sequence. So effectively, what this plot shows is we know of over 100 of these planets, and most of these planets are closer to their stars than Jupiter is to the sun. But we also know that Jupiter, Saturn, Uranus, and Neptune would eventually appear on this plot towards the right end. All these planets around giant stars are, in fact, giant planets. We don't actually know of terrestrial planets yet. And we also know of 4 planets that orbit white dwarfs. So why 4? Well, it's because they're hard to find. But the point is that we now have populations of these giant planets that span different stages of stellar evolution around both giant stars and white dwarfs. And the question that we addressed is, how do the planetary magnetospheres change with time as the star evolves? So our focus was to measure the change in the magnetopause standoff distance, which we denoted as d of t, as you see in the diagram. Now, this d is the Ferraro-Chapman distance that Fran discussed earlier. And we also denoted the planet's radius as r, and we didn't need to specify actually whether the planet is a giant planet or a terrestrial planet or some mix of the two. And we computed this variation in d by balancing the ram pressure of the stellar wind and the magnetic pressure of the planet. So as the star leaves the main sequence, the stellar wind changes both in its density and in its velocity. Also, the wind pushes outward the orbit of the planet. And this plot illustrates on the y-axis the extent to which the planet orbit expands, starting at a distance of 5 AU. So on the x-axis, time is measured from the age when a star is born, and the numbers on the top of the curves correspond to the main sequence stellar mass value. So the sun is the rightmost curve here. And that curve shows that the sun takes about 12 billion years to leave the main sequence, and the curve shows that Jupiter is going to be pushed out to about 10 AU. Now, while these planetary orbits are expanding, the stellar wind will be changing. And this plot displays the extent to which the wind density changes at the location of the planet. So the long vertical features demonstrate that the density, the wind density, may change by up to about 10 orders of magnitude. And this plot here illustrates the change in wind speed. So as you can see, this speed varies from a few kilometers per second to a few thousand kilometers per second. So having prescriptions for how the wind changes with time then enabled us to achieve our goal of finding this magnetopause standoff distance. Now, the first equation shown here provides the balance of ram pressure of the stellar wind and the magnetic pressure of the planet. And the second equation gives the wind velocity as some multiple of the escape speed at the surface of the star. And the third equation gives the wind density, assuming spherical symmetry in the ejection of the wind. And then the final equation gives the orbital expansion of the planet due to stellar mass loss. So analytically, combining these 4 relations yields the following result. where we were able to express the magnetopause standoff distance d as a ratio with planet radius r equaling a product of two terms. And one of these terms is the time-independent c constant, and this other term is this time-dependent f of t function. And this formulation helped us to characterize our results by determining maximum and minimum bounds. So just to remind you of the geometrical meaning of d of t and r, here's the schematic illustration again. So what are the results? Well, here is one example where a planet with a magnetic field strength of 10 Gauss is initially at 50 AU. And this plot shows its magnetopause distance evolution around a 1.5 solar mass star. And the abbreviations RGB and AGB refer to two different stages of giant branch evolution. The abbreviation PN refers to the planetary nebulae phase, where the stellar mass is largely fixed, but the radius rapidly contracts into a white dwarf. And WD stands for white dwarf. So the plot shows that the planet's magnetosphere varies in size and is actually quenched for brief periods of a few million years in between stellar phases. Now, white dwarfs have no winds at all, and so around those stars, ram pressure would not confine a planetary magnetosphere. However, if the white dwarf itself is sufficiently magnetic, then that field alone could provide the external pressure necessary to balance out the magnetic pressure of a planet. So that's just one particular example. This plot here shows 11 examples simultaneously, again with a planet containing a magnetic field strength of 10 Gauss and initially at 50 AU. And as you can see, regardless of the stellar mass chosen, which are the numbers at the top of each curve, the maximum magnetopause expansion distance varies by a factor of 2 and 3.5. So with our formalism, we can also ask some meaningful questions about the minimum necessary magnetic field strength of a planet to satisfy certain conditions. So the first question is, can a planet host a magnetosphere at any point during the giant branch phases? And the answer here is given by the lower set of curves, where each line corresponds to a different stellar mass. And overlaid on those lower set of curves is Jupiter's current magnetic field strength on the black horizontal line, which is 4 Gauss. And because Jupiter's location is at 5 AU, its magnetosphere would just barely survive the sun's post-main sequence evolution if Jupiter's magnetosphere will be as simple as we have modeled it here, which it won't. The next question we can ask is, how strong must the planetary magnetic field be in order to maintain a magnetopause standoff distance, which is at least double the planet's radius? And the answer is provided by the upper set of curves. These values, for the solar system at least, would be unrealistically high. So overall, the high values of the planetary magnetic fields that would be required to provide protection suggest that planet atmospheres and surfaces will nearly always be exposed to this erosive giant branch radiation. And finally, we can also relate the magnetopause standoff distance variations to the prospects for maintaining habitability on terrestrial planets. And this plot illustrates how the habitable zone distance expands and contracts due to giant branch evolution. And in nearly all cases, the expansion of the habitable zone, here represented by a single distance, it's faster than the expansion of the planetary orbit, which recall is a factor of just 2 to 5. Whereas here, the habitable zone expansion factor is 5 to 40. So hence this fast movement of the habitable zone and the quenching of planetary magnetospheres suggests that currently potentially habitable planets orbiting white dwarfs would have previously been inhospitable. So in conclusion, we model the fate of planetary magnetospheres after the parent star leaves the main sequence. And our formalism is general enough to apply to any type of planet. And we found that most exoplanets will struggle to continuously maintain their magnetospheres during the giant branch phases of evolution. And finally, we found that exoplanets with field strengths less than about 0.1 Gauss cannot maintain their magnetosphere really at any time around evolved stars. So thanks for your attention.
Thank you. We've got plenty of time for questions. If you'd like to raise your hand and we can get to them or put them in the chat. We've got one from Offa. What would be the effect of the internal planetary magnetic field?
We didn't model that, and I don't know. There's detail that are in solar system magnetosphere studies that that we just did not include here.
Yeah, hi, Dimitri. I have a question too. It might be a little bit similar to Ofer's. So it was really nice to see sort of this back of the envelope estimate of what would happen to magnetospheres. What's your guess about some of the internal constraints on magnetospheres? You know, we just talked about the interior dipole evolution, but there's also planetary outgassing and things like that, all of which will presumably kind of decline with time. Is there some sweet spot in planetary and magnetosphere and star co-evolution?
Well, as we've already seen, there's a lot of interest and a lot of literature about atmospheric escape around exoplanetary systems. And so combining those studies and those constraints with these more back of the envelope calculations might be able to provide some progress. And I mean, for example, we know that a young white dwarf is much stronger in terms of its XUV radiation to evaporate atmospheres than a star, a precursor star during the giant branch phases, and those types of studies might be able to help. But as you've seen here, we've really just taken the simplest possible approach, just because of our lack of knowledge of these of many of these exoplanets, just as a starting point. But I think future studies would definitely benefit from more detail.
Yeah, thanks. Simple is the right place to start, I think.
Adele, if you'd like to go ahead and ask your question.
Sure. In your simulations, do you consider input from the ionosphere and atmosphere? And how could such variations influence the long-term variations of planetary magnetospheres?
So no, we did not include that. The variation in our simulations really came from the star rather than the planet, because our planet, I mean, we just modeled it as you see here. We didn't even have to specify it was a terrestrial or giant planet, just as a sphere with radius r. So so really the interesting detail here came from the change of the star, and you know, and any future studies about the planetary about the ionosphere would you know, they would have to be left for the future, unfortunately.